418, analogy of closest packing periodic table and atomic structure. 418.1. The number of closest packed spheres in any complete layer around any nuclear group of layers always terminates with digit 2. First layer 12, second layer 42, third 92, 162, 252, 362, and so on. So Fuller's formula is the layer squared as a 10, so 1 squared in the tens column, and then plus 2. So this is 1, you get 12. This is 2 squared, 4. The second layer is 42. 3 squared is 9, you get 92. 4 squared is 16, 162. 5 squared is 25, 252. 6 to the second power is 362. The digit 2 is always preceded by a number that corresponds to the second power of the number of layers surrounding the nucleus. The third layer's number of 92 is comprised of the 3 multiplied by itself, i.e. 3 to the second power, which is 9, with the digit 2 as a suffix. 418.02. This third layer is the outermost of the symmetrically unique nuclear system patterns and may be identified with the 92 unique self-regenerative chemical element systems and with the 92nd such element, uranium. Here's a periodic table of the elements. The first 92 are more stable and present in nature. So up to the number 92, which is here, uranium. It's just on the bottom because I'm sure, as you know, but it's worth reiterating. You have 1 and 2 opposite poles. And by the way, there's a lot of literature about that this might not be the right way to show 1 and 2 because they're kind of excessive. But then 3, 4 are here, and 5 to 10 are over here, and 11, 12 are here. And these numbers reflect how many protons are in the nucleus, which then determines the electron orbitals. And so the similarity when you look at a column, and that's why Mendeleev named it a periodic table. So then in that 19, suddenly you get a new orbital in, and so they tuck it in here, 21, 30, and you get out to 36. The next row of 37, you go out to 54. And now, because it wouldn't fit on a page, if we had put this in, everything would have been pushed over. You tend to draw it on the bottom, but so it's 55, 56, then 57 through 71, and then 72 up to 86, 87, 88, 89, 90, 91, 92. He's now going to compare that in this section of synergetics. He's going to compare that number 92, which seems really important, to this number 92, which is the third layer. The closest sphere packing system's first 3 layers of 12, 42, and 92 add up to 146, which is the number of neutrons in uranium, which has the highest nucleon population of all the self-regenerative chemical elements. These 146 neutrons, plus the 92 unengaged mass-attracting protons of the outer layer, give the predominant uranium of 238 nucleons, from whose outer layer the excess 2 of each layer, which functions as a neutral axis of spin, can be disengaged without distorting the structural integrity of the symmetrical aggregate, which leaves a chain reacting uranium-236. The stable uranium is 238. I'm not sure of that. So let's just do it this way. Uranium-238 is the most common isotope. Okay, so that is the one that is found with an abundance of 99% in nature. Then the other isotopes are named 235 and 236. And when you name it differently, what you're doing is counting neutrons. So this is an isotope that is neither fissile nor very good fertile, and it's considered a nuisance. And long-lived is found in spent nuclear fuel. So I guess it's a little more stable. He has added up the 3 spheres, and I'm smiling because I wouldn't have thought to do that. And that adds up to 146, which is what gets you to the 238. So number 92 is really the number of protons, and then you've got 146 neutrons. And so in a kind of poetic nature, because it's hard to interpret what this means in physics, this number does match this. And so Fuller's brain, it's very important that -2, it becomes 236. So notice he says here that's chain reacting. And here in this article that we just looked at, 236, they actually consider it a nuisance. And we could look more at what is the most reactive. The last thing I want to annotate here is again, a theme of Fuller's. When you have two showing up, Fuller likes to relate that to the fact that if you spin any system, it will spontaneously generate two important poles. And so whenever Fuller smells a number two, he will want to say, oh, this must be due to spin.
All the first 92 chemical elements are the finitely comprehensive set of purely abstract physical principles governing all the fundamental cases of dynamical, symmetrical, vectorial geometries and their systematically self-knotting, i.e. processionally self-interfered, regenerative inward shunting events.
I would translate this as follows. The first 92 are very important to Fuller in their stability. And so when Fuller considers the stability of these things that we find in nature, he then poetically calls them knots. So you think of an energetic world where everything's going at the speed of light, and then you think of light not in a knot, and that's mass. Now, that is many people who read Fuller come away with that idea. It's a powerful idea, but it's difficult to map that to all our conventional understanding. But if you go with that, then this chunky sentence is saying that these are stable knots of energy. They are finitely comprehensive. They're purely abstract physical principles governing all these cases. And why do we sense them? Why can we measure something and say, oh, here is carbon? Why is it that we can measure something and say, here's nickel and cobalt? Because they are pattern integrities, because they self-interfere, regenerative, they're constantly regenerating themselves, they're coherent, inwardly shunting events. They are a system.
Run 5.
5.
Yeah. The chemical elements are each unique patterns of integrities formed by their self-knotting, inwardly precessing, periodically synchronized self-interferences. Unique pattern evolvement constitutes elementality. What is unique about each of the 92 self-regenerative chemical elements is their non-repetitive pattern evolvement, which terminates at the third layer of 92. Independent of their isotopal variations of neutron content, the 92 self-regenerative chemical elements belong to the basic inventory of cosmic absolutes. The family of prime elements consists of 92 unique sets of from 1 to 92 electron-proton count inclusive and no others.
And he's stating quite clearly what we covered when we started the section, that from 1 to 92 is uniquely stable. And then Fuller, because he's always thinking of an energetic world, calls them self-regenerating, which I do think maps to conventional thinking, but it's not typical conventional thinking. So in conventional thinking, you take a chemistry class and they say, here's carbon. They don't think of carbon as energetically coherent. But carbon is a very busy place. It's got neutrons and they're all made up of quarks and everything's moving around. Whenever you see diagrams of it, everything's in constant motion. And so Fuller focuses on the self-regenerative aspects of that.